Hey there, so next we're moving into section 4.4 where we look at derivatives of exponential functions. All right, so as you've seen in the past, exponential functions are amazing functions with tons of applications in biology and the life sciences and all over science in general. Okay, so in order to come up with the derivative of exponential functions, we want to go back to the beginning. We want to actually explore and not forget where derivatives come from, the limit definition of the derivative. So as we develop rules for how to find derivatives of more complicated functions, remember that we always go back to that limit definition. So it's important to remember how far we've come and where we've started. Okay, so we're going to do that. Let's find the derivative of the exponential function f of x equals e to the x using the definition of the derivative. So as we're doing this, we're going to run into some weird problems and we're going to want to do some interesting algebraic manipulation. So recall that the definition of e is the limit as n goes to infinity of 1 plus 1 over n to the n. Okay, we explored that a little bit in the exponential and logarithm section. Okay, now an equivalent definition that we haven't talked about, but this is an equivalent definition of e, is the limit as n goes to 0 of 1 plus n to the 1 over n power. So very similar looking, but we're going to 0. We still have a little weird divide by 0 situation, but remember that limits, you're not actually plugging in 0, you're approaching 0. So this is an equivalent definition of E. So I wanted to mention this one because we're going to take advantage of this one in the process. Okay, so we'll be on the lookout for an expression that looks something like this. Okay, so let's go ahead and work out the limit definition. So f prime of x, or d over dx of the e to the x. Okay, the limit definition. So the limit as h goes to 0 of f of x plus h minus f of x over h. Don't forget that thing, okay? Maybe you were hoping you'd never see it again, but there it is, the limit definition. So the limit as h goes to 0, okay, f of x plus h, so that's e to the, plug it in, so now it's x plus h up there, minus e to the x. So how do we deal with this now? Okay, a lot of times when we're dealing with this, the x plus h thing is the main issue that we have to deal with. So with polynomials, we had our processes. With radicals, we had our processes. For this, it's going to be a little bit different. So the first thing to do is remember that if you've got two numbers with the same base multiplying together, their exponents can add. So I'm actually using that in reverse order. So if I've got e to the x plus h, that's the same as e to the x times e to the h. Remember that the powers add when you multiply two bases together, as long as it's the same base. Okay, so kind of just using that property in reverse. And then now that I've done that, we notice that e to the x is like the GCF of the numerator, so we can factor it out. Another thing to keep in mind is that since this limit is all talking about h approaching 0, it doesn't affect x at all. And so when we factor out that e to the x, we can actually bring it all the way out in front of the limit. Since this limit is changing h, it has nothing to do with x. So then we're left with e to the h minus 1 when we factored out that e to the x. Okay, so now we have a little bit of a weird situation right there, because if we try to do our direct substitution, we end up with 0 divided by 0. So we got to do some fancy stuff here. So notice that, yeah, as you plug in 0, you get e to the 0, which is 1. 1 minus 1 is 0. Plugging in 0 in the denominator, we get 0 over 0. So that's that indeterminate form. Okay, so in the past with polynomials and square roots, we would try to factor and cancel or multiply by the conjugate or something to hopefully get it to reduce and cancel. But here we don't have those options because we're dealing with exponential functions for the first time with these derivatives. So we're going to do some very fancy algebra and substitutions to change how it looks. And remember, the goal is to see if we can rewrite E-type stuff with this definition here. Okay, so let's let n equal the numerator. Okay, so n equals e to the h minus 1. So this I want to turn into an n. Okay, but I also want to replace all of the h's. So the denominator there, I need to get a replacement for h. So let's solve this substitution equation for h. So let's add 1 to both sides, and so we could get e to the h equals, if we add 1 over there, we get n plus 1. And then to get this h by itself, we would have to take the natural logarithm of both sides. So if we take the natural logarithm of e to the h equals the natural logarithm of n plus 1, remember that the natural logarithm of e to a power cancels out and you get just the power. So a little bit of a mess, but the h on the bottom is now going to be rewritten as the natural log of n plus 1. Okay, and in the spirit of substituting everything for h, we want to also realize that as h goes to 0, we can see that n also goes to 0. And that is with our substitution here, if we let h go to 0, that's going to be e to the 0, which is 1. 1 minus 1 is 0. So as h goes to 0, n also goes to 0, or vice versa. Okay, so all of these substitutions in mind, we can rewrite the limit using these substitutions. So picking up where we left off, okay, this step here, I wrote it down here again. Okay, so we're picking up where we left off. That e to the x is still just going to hang out in the front. But now all of our substitutions are in place. Instead of h go to 0, we're going to go n goes to 0. Instead of that numerator stuff, that substitution becomes the n, and then that denominator of h, that substitution becomes the ln of n plus 1. Okay, so why in the world did we do all of that? Well, you're going to see we're trying to build toward that e definition thing. Okay, so let's continue to do some manipulation here because we still have a 0 divided by 0 problem. So I'm going to multiply the numerator and denominator by a big fancy 1. Okay, 1 over n over 1 over n. So 1 over n multiplying onto that n cancels and becomes a 1. 1 over n on the denominator, I'm just going to write it in the front here as 1 over n times that natural log. Okay, now we want to take advantage of some log properties now. So recall that if you've got a number times a log, then you can rewrite it with the power rule as the log of the stuff raised to that power. So recall, and maybe I'll just write it, I don't know what letters we used in the past, but if you have a times natural log of x, remember that that power, or that number in the front, can become a power, and we can write that as ln of x to the power of a. Okay, so I don't know what numbers or what letters we used in the past, but that's pretty much just the power rule. So that's what I'm using here. This 1 over n multiplying in the front of the natural log, I'm going to put that 1 over n as a power of the stuff that was inside. And so I use these extra parentheses to indicate that that 1 over n is a power on all of the stuff that was in there. Okay, this is looking pretty good. This is starting to look like this e definition. Okay, now that's 1 plus n. We currently have n plus 1, but same thing, we can just rewrite the order with addition, makes no difference. Okay, but then also remember our limit rules that we came up with. If you have the limit of a fraction, it's the same as doing the limit of the numerator and denominator separately. Okay, so that's just what I did here. I split the limit separately. Okay, and then remember that if you have the limit of a constant, right, there's no n involved with this 1. So as n goes to 0, 1 just stays a 1. Okay, and then the limit of a log, assuming that everything exists, the limit of a log is the same as the log of the limit. So that was another one of our limit rules. So we can just pass this limit onto the inside. And again, I rewrote the n plus 1 as 1 plus n on purpose because now look what happens. When we pass that limit onto the inside of the log, look at this. It took a whole bunch of crazy manipulation, but this limit as n goes to 0 of 1 plus n all to the 1 over n power, that is exactly our alternative definition of e. Okay, so it took some crazy manipulation to get there, but now this limit on the inside of the log, that is exactly the definition of e. And so we can write that as ln of e down there. Okay, and then remember that natural log of e is just 1. And so we have 1 over 1, which is 1. And so that e to the x that was hanging out in the front all along is still there, and it just multiplies with a 1. And so the result is e to the x. And it's like, wait a minute, what did we just do? We applied the limit definition to e to the x, and after all of this crazy fancy manipulation, it came out e to the x. So the derivative of e to the x is itself. Did you just get chills? All right, that's actually an amazing result. We worked it out very, very specifically, the whole limit definition of the derivative of e to the x, and when everything was said and done, it simplified all the way down to itself, which is absolutely an amazing result. Okay, that's one of the reasons why that E number is one of the most powerful, crazy numbers in all of mathematics. Okay, so that is the actual result. The derivative of f of x equals e to the x is itself. Oh my gosh, just totally crazy that that happens. Sorry if I'm geeking out a little bit, but that is just absolutely amazing. So can you think of, just kind of as a philosophical question, can you think of any other function where the derivative of that function is itself? Okay, think about it. I'm not going to answer that question. I want you to kind of think about it because it's very interesting. This does not happen very often where the derivative of a function is itself. Okay, so I think I will make a separate video to pick up on the next stuff, and then we'll start doing some actual derivatives of exponential functions.